So here we are at the beginning of chapter 15. So chapter 15, Chemical Equilibrium, is the first in 3 chapters that are all very much connected. So chemical equilibrium, this idea of equilibrium, we saw a little bit in chapter 14. That was when we saw these arrows that went forward and backwards. When we were doing our mechanisms at the end of the chapter, we're going to be focusing on that. Now, chapter 15 is giving us the basics, giving us an understanding, teaching us the words, starting to solve problems with equilibrium. And then in chapter 16, we're going to use everything from chapter 15 and apply it to acids and bases. And then chapter 17, which is my favorite chapter title of all time, which is Additional Aspects of Chemical Equilibrium. They couldn't even come up with a name for it because it's just the rest of the equilibrium stuff. So chapters 15, 16, and 17 are really all one giant chapter that has been chopped into thirds because otherwise it would be too big of a chapter. So I'm just giving you that heads up because that makes it even more important that as we're going through chapter 15, when you have questions, you ask them because this is really not going away at all. So just make sure you're open if you have questions, comments, concerns as we move through this, because everything from chapter 15 you use in 16. Everything from 15 and 16 we'll use in 17. So it just keeps growing. Okay, so to get us started, here's our chapter 15 objectives. Again, this is for the entire chapter, so things that you need to know how to do by the end. This would be what I would focus on when you're studying for exams. So, definition stuff. There are 2 types of equilibrium. There is static equilibrium, which is what happens when we have forces on an object that keeps it stationary. So this super fancy picture of 2 gnomes on a log, like a seesaw, where they're balanced completely flat. That would be static equilibrium. We don't care about static equilibrium in chemistry because in chemistry, things, atoms, molecules, they don't stop moving until we get to 0 Kelvin. But we're going to be focused on dynamic equilibrium. Now, I didn't put the definition here, I'm realizing right now, but dynamic equilibrium is when a process is happening in 2 directions at the same speed, at the same rate. So it looks like nothing is changing, but really it's happening forwards at the same time it's happening backwards. So it's constantly occurring, but we don't see an increase in things in the left or the right. So dynamic equilibrium, an example of that that's not related to chemistry would be if we had a really popular bar, okay, and it was Saturday night and it was warm outside and they were at capacity. So the bouncer at the bar, there's a line of people waiting outside. Let's say there's 10 people waiting outside the bar, waiting to get in. The bouncer is not going to let anyone else in until someone leaves because they're at capacity. So let's say 2 people that were in the bar choose to leave, so they walk out the door. The bouncer lets 2 people that were in line from outside into the bar. And let's say the capacity of the bar was 150 people. So there's 150 people inside the bar. And before the people left, there were 10 people outside the bar. Well, 2 people left and 2 people went in. So when that happened, there were still 150 people inside the bar. 2 people left and 2 people went in, but if I still counted the total number of people, it would be the same. Now, outside the bar, there are still 10 people. 2 individuals went outside at the same time 2 individuals went inside. So sure, they're not standing in the same location, they're not the same people, but if I just counted the number of human beings, when 2 people went in and 2 people went out, there's the same number of human beings both inside the bar and outside the bar before and after that happened. So that's an example of dynamic equilibrium, or how we can see dynamic equilibrium. At dynamic equilibrium, the amounts of, for us, we're focusing on chemical reaction, so think of like reactants and products. Once we're at equilibrium, those amounts stay the same. Now, it could be that all night people keep going in and going out of that bar. But all night there would be 150 people inside. Okay. So chemical equilibrium, when we're looking at a chemical process, it's when the reaction rate going forward and the reaction rate going backwards are equal. And again, the way we can recognize that something can go to equilibrium, or we see these arrows going forwards and backwards, which gives us the information that the reaction happens from reactants to products and products to reactants. And even though the reaction happens both ways, we're still going to call the things on the left the reactants and the things on the right, the products, even though they both react. But just to keep things the same as what you learned in Gen Chem 1, those are the terms we're going to use. Okay, so when a reaction is at chemical equilibrium, it happens the same speed going forwards as it does going backwards. Okay, so another term for this is it's reversible. So only reversible reactions can have chemical equilibrium. They can only go to equilibrium if they can happen forwards and backwards. Now, at equilibrium, that does not mean that the amount of reactants and the amount of products are equal. Nope. We have no idea how much reactants and how much products there are. But what we do know is at equilibrium, those amounts stop changing because the reactants, when they form products, that happens at the same time the products are forming reactants. So the concentrations are not equal of reactants and products, but they stop changing. And what's occurring is the reaction's continuing. It's just happening at the same speed forwards and backwards. So from the big scale perspective, it doesn't look like it's happening, but it never stops. That's why it's always dynamic equilibrium. The reaction continues forever and ever. Okay, so we already saw this in the last chapter, but these double arrows are our symbol for when a reaction can reach equilibrium. Okay, and so the reaction can have it goes in the forward direction and the reverse direction. So this is something from chapter 14 going forward. So if we look at just the forward reaction, the left to right, the reactants to products, if this was an elementary step, if this is actually the way the reaction happened, it was the mechanism, we could write the rate law, right? The rate law is rate equals K times the reactant, and then you count the number of reactants, and that goes the power there. So that's first order. Okay, that only if this is an elementary step, and I'm saying that it is. So let's look at the rate law for the reverse reaction, the backwards reaction. So when I'm going this direction, okay, I just rewrote it here. And so then the rate law is rate equals K times NO2, and there's two of them, so that becomes second order. Okay, so when we were doing this in chapter 14, we used this to help us substitute to get rid of the intermediates. And we set the forward and the reverse rate laws equal to each other. So we could do that again. But this time, I'm going to rearrange it differently. I'm going to set the forward rate law and the reverse rate law equal to each other, and then rearrange it to get the concentrations, the chemicals, the N2O4 and the NO2 on one side, and then the rate constants on the other side. Okay. So I guess before we do that, this is just showing when equilibrium hits. So that dotted line is showing us when equilibrium hits, and that is being represented when the rate forward is equal to the rate reverse. Now notice, even though that reaction had been written at equilibrium, like there was equilibrium arrows, when the reaction started, it wasn't at equilibrium. When the reaction started, the reverse direction was basically there was no speed. It wasn't going fast. There weren't any products. So at the beginning, it was really just the forward reaction happening, and then the forward reaction started slowing down because the reverse reaction started occurring, and it started speeding up until they met in the middle. And once they hit that same concentration, the same rate, they're going to hit equilibrium, and then notice that they don't change. Once it hits equilibrium, it's going to stay at equilibrium until something messes with it. Okay. So that's the graph where we're looking at the rate of the forward and the reverse reaction. Here's where we're looking at the concentrations of the two chemicals. So this one is the product. So the orange is the product and the blue is the reactant. So at time 0, they have very different concentrations. What this shows, the product has a 0 concentration. That means they didn't start with any. At the beginning, they only put the reactant in the container. Okay. The amount of reactant is decreasing because it's reacting, so it's going away. The amount of product is increasing because it's reacting and it's being formed. Now, once it hits equilibrium, which is that dotted line, which would be at the same time as that previous graph, notice that the molarity of NO2 and the molarity of N2O4, they're not the same concentration, right? The Y value is not the same. But once we hit equilibrium, it stops changing. So if we're looking at concentration, we would not look for the concentrations to be equal to tell us when we're at equilibrium. Nope, we're looking for when the concentrations stop changing. So the thing that's equal at equilibrium is the rate. The rate forward and the rate reverse are equal to each other. The concentrations get to a steady spot and stay there. Okay. So back to our reverse and forward rate law. So I just set the reverse and the forward equal to each other, and then I'm going to rearrange this to get the lowercase letter k's on one side and the molarities on the other. So that's all that happened, is I rearranged this equation. Okay, so on the left-hand side, this is the rate constant forward divided by the rate constant reverse. Well, both of these are constants. So that is just a constant divided by a constant, which is just a number. Now, this is a ratio. We don't know what those values are. Okay, so this is one of those times that if I was in charge of chemistry, I would have made different decisions here. But the ratio of the forward rate constant divided by the reverse rate constant. These are the rate constants from rate laws. That ratio, we are now going to call capital letter K the equilibrium constant. Yeah, they picked the same letter. The difference are the rate constants are lowercase letter k, and the equilibrium constant is capital letter K. Couldn't they have at least chosen a letter where the lowercase and the capital letters look significantly different from each other, like Q or something? But nope, capital K and lowercase letter k. Okay, so rate constants are part of equilibrium constants, but kind of from here on out, we're not going to be dealing with rate laws and rate constants in chapter 15. We're going to go with capital letter K as the equilibrium constant, and we're going to be focusing on that it's equal to the ratio of, the way this works, products divided by reactants, where the powers, the orders, come from the coefficients. Okay, so here's a generic equation, right? Just capital letters are chemical symbols, lowercase letters are coefficients. So if I wanted to write the equilibrium constant expression, the capital letter K expression, like it was on the previous slide, it's going to be products divided by reactants. So what this would look like, products, C and D, raised to their coefficients, divided by reactants, A and B, raised to their coefficients. Now, all of a sudden, magically, this capital letter K, this equilibrium constant, got a subscript C. C, in this scenario, stands for concentration. And when we're dealing with equilibrium, the only concentration unit we're going to deal with is molarity. So we see these brackets around C and D and A and B, and that stands for the molarity. So that's the molarity of C raised to whatever power, the molarity of D raised to whatever power, divided by molarity of A raised to whatever power, times molarity of B. Now notice in here, it's all multiplication and division. I know in the balanced equation there's addition signs right there, pluses. In the equilibrium constant, it's all multiplication and division. Okay, so in Kc, you would plug in a molarity, a molarity, a molarity, or molarity. They're raised to some power, and we could solve. So you would think that the equilibrium constant, the number that we would get here, would be some value of molarity. Nope, it's always going to be unitless. We're going to come back and look at that more later. But no matter what, equilibrium constants have no units, which is different than rate constants. Okay, so if we have the molarity of our chemicals, we would calculate the Kc, the equilibrium constant, using concentrations, using molarities. Now, if we have the pressure, which the only unit for pressure we're able to use is atmospheres, it looks the same. It's just that capital letter P stands for pressure. But it's still products over reactants, where they're raised to that power. And then we have a subscript P instead of C. Okay, so let's just summarize here quickly the differences between the letter K's. So the rate constant, which came from chapter 14, is part of the rate law. It has units, but they vary, right? That was we had to solve for the units to see what they were. They had molarities in seconds, like inverse molarity, inverse seconds, or just inverse seconds, whatever it was. It is temperature dependent and reaction. I guess it's temperature and reaction dependent. Okay. So the equilibrium constant, it is only for equilibrium reactions. It has unitless, so it's just a number. It is temperature and reaction dependent, but even more specifically, we have two types. Kc, which is using molarity in brackets, and Kp, which means we have atmospheres, and we're using the capital letter P. And it's going to follow the format products over reactants. We're going to need a lot of chances to practice this. Oops. Really doesn't want me to write down here. That's beautiful. Okay. So, lowercase k and capital K are not the same thing. We're not going to see much of lowercase k in chapter 15, 16, or 17, but it helped bring us to capital letter K. Okay. So, looking back at this real quick, I said there were two types, right? KC and KP. Well, if I calculated the equilibrium constant using molarities, and then I took the same reaction, and I calculated the equilibrium constant using atmospheres, we would not get the same answer, just because molarity and atmospheres are different units measuring different things. So for a reaction, its Kc value is almost always different than its Kp value. But what happens if I know the Kp value, but for whatever reason I need the Kc value? Well, then I need the equation on how to convert those. So that's what we're going to look at here. And to do that, that equation is derived from the ideal gas law. The ideal gas law just seems to never die, right? Pivnert, it looks like pervert, but it's not. So what I did here is we don't have molarity in the ideal gas law, but I can take moles and liters and take moles divided by liters, which is the closest thing we have to molarity. So that's like molarity. And that's pressure. Okay, those are the things that our Kc and Kp values are comparing. Now R is 0.08206 liters atmospheres per mole Kelvin. Okay, and T is temperature in Kelvin. So that's the ideal gas law. So I'm going to do some magic and give you the equation that compares Kc and Kp from this. So here's the equation, which would always be provided for you, okay, to convert Kc to Kp or Kp to Kc. Okay, now again, R is 0.08206 liters times atmospheres divided by moles times Kelvin. You will be given this equation. It's not to memorize. You'll be given this constant. But it would be expected that you could, from that information, do the math. Okay, so the temperature needs to be in Kelvin. Kp is just the equilibrium constant with pressures, and Kc is the equilibrium constant with molarities. Fine. The only weird thing here is delta N. Now, N in the ideal gas law stands for moles. Okay, and delta means change. So this is the change in moles. Now it's raised to the power of. So R and T multiplied together are raised to the power of this delta N. So delta stands for change, N stands for moles. Now more specifically, in this case, it stands for moles of gas. That is important because Kp is only going to be impacted by gaseous reactions, and so it's going to matter the moles of gas. So when I do delta N, it's going to be the moles of products that are gases minus the moles of reactants that are gases. So we're going to do one example because I want to especially practice the delta N thing, but it is important that it's specific to just gases. So let's try this. Let's get a reaction. Let's convert between Kp and Kc. So here's my reaction. And we know the Kc, which is 1.08 times 10 to the 7th. And we're told the temperature is 700 degrees Celsius. And from this information, we need to calculate the Kp value. Well, I know this is the equation I need to use. Kc is easy to plug in there. R is that 0.08206 liters atmospheres per mole Kelvin value. T is the temperature, and it needs to be in Kelvin, which means I do need to convert this to Kelvin by adding 273.15 to it. That's great. So I have an R and a T, and I have a Kc. Now delta N. Delta N is the change in moles of gaseous products. Just a reminder, these are the products and these are the reactants. So what we need to do is look at this and calculate or figure out, it's not a whole lot of calculating, but how many moles of products are gases? Well, this is a gas and there are two of them. So for delta N, the moles of gases that are products are 2. Now reactants, that's a gas and that's a gas. So how many moles are there? Well, there's 2 of hydrogen and there's 1 of sulfur. So 3. So delta N would be -1. So when I do this, Kc, 1.08 times 10 to the 7th. I just plugged that there. R, 0.08206, constant. The temperature, 973.15 Kelvin. And then they're raised to the -1 power. Now I just need to grab my calculator. Now I have to do parentheses first. So 0.08206 times 973.15, multiply those together in my calculator, raise them to the -1 power, and then multiply that by 1.08 times 10 to the 7th. And what I got was 1.35 times 10 to the 5th. It's a different number. Okay. Let me backtrack. And let's say, just to pretend, this was a solid. If that was a solid, I want us to calculate the delta N for my new scenario. So change in moles of products. So products, that's a gas, there are 2. Now reactants that are gases, well, that's a solid, so I ignore it. That's a gas, so there are 2. Oops, minus. So my delta N would be 0. So when we're doing this, things that are solids, liquids, or aqueous things, we ignore them when we do delta N. Okay. Again, you would be given this equation, you would be given R, you would be given a balanced equation and a temperature, and given either Kc or Kp and asked to solve for the other one. That's how these problems are going to go.